Hello everyone, I am Yashwant Yogi and today we will be discussing PARTE questions for week 12 for Chem 115. So a suggestion before starting, if you haven't solved the PARTE questions, please do try them and then come to this video. It would be better that you solve your by self and then try to check your answers here. So here we start, moving to question number 1. So the question states, what is the formal charge on carbon in preferred structure of CO2? So there are two important stuff that we need to know, that is formal charge. Here you go. What is asked is formal charge on carbon and in the preferred structure. So it's called preferred. Okay, that is the most important structure of CO2. So what we have to do is we have to make the structure of CO2 first. So considering CO2, you can see that C is the least electronegative element out of C and O. So we will place that in the center. Now, to understand what kind of bonding they will be forming, first we will make 1-1 bonds with each oxygen. Now, what we can do is we can count the number of electrons, the overall electrons. And here you go. So it's C has 6 valence electrons. Sorry, it has 4 valence electrons. Similarly, oxygen has 6. There are 2 oxygens, so we'll multiply it by 2. And now we have a total of 16. We have already made 2 bonds, so we will subtract 4, 2 for each bond, so that we have 12. Now we will distribute these 12 electrons between the oxygen as we usually do, and there you go. But now when you check whether the central atom C, do you think that it follows an octet rule or not? So if you see, it has right now only 4 electrons, so we need to give this more electrons to carbon to form the octet. So then what we do is we create double bonds, and then you have something as C double O, and what is left with oxygen is just 2 pairs of lone pair electrons. And now you can see that carbon is having octet. And to check the formal charge, so how do you check the formal charge? What does it mean? So we are comparing in formal charge, we are comparing what the initial situation was compared to the present situation in this structure. So carbon initially had only 4 valence electrons, right? So we will check whether it has 4 electrons now. So when we are seeing a bond, you can see that in each bond there are 2 electrons. Okay, so when we have 2 electrons, each electron is from one of the atoms. So 1 electron was given by oxygen, 1 was given by carbon. So each bond can be considered as equivalent to 2 electrons and 1 electron from each side. So if you see, carbon now has 4 electrons anytime with him, like on his own side. So you can say that at present it has 4 electrons. So the formal charge, if you know, it says that number of valence electrons minus number of bonds, and in bracket we have lone pair electrons. So we know that the number of valence electrons were 4, number of bonds are 4, and plus the lone pair is 0. So the formal charge would be 0. So we can say that carbon has 0 formal charge. So the answer is A. Now moving to question number 2. So in this question we are trying to understand something about resonance. So let's read the question first. The number of equivalent resonance structure, it's equivalent resonance structure connected with the best Lewis structure of SO3 is. So we have SO3, we have to see the best Lewis structure. So we'll go with the original way. We'll count the number of electrons, and if you see out of SO3, we have S as the central atom because it's the least electronegative out of S and O. We'll first check the number of electrons. So it's S has 6 valence electrons, oxygen 2 has 6, and then we have 3 oxygen, so it's multiplied by 3, it's 18, so the total is 24. Now we will make each bond with each of the oxygen from sulfur, so consider making something like, we're just making a general way, so equally. Then for each bond you can subtract 2, so it's minus 2 into 3, we have 3 bonds, so it becomes 18. Now we can distribute this 18 electrons between 3 oxygens that are outside, so it becomes 6 electrons per oxygen, and do it like this. We can see that S is not having an octet here, it has only 6 electrons, but if you see oxygen, it's satisfied. But there's another thing. If you check the formal charge on each one of them, you will see that oxygen right now has 7 electrons, so it's someone here and here, so 6 of the lone pairs and 1 from the bond, so indirectly it has -1 formal charge. Similarly, other oxygen also has 1 formal charge. If you check for sulfur, sulfur initially had 6 electrons in the valence shell, but right now while sharing it has only 3, and there is no lone pair, so we don't have any. I'm using the same formula that I mentioned here, this one. So you have 3 positive charge, so it's positive, so it has positive charge. But if you know that we don't want any charge distribution, the overall charge is still 0. You can see 3 and minus 1 3 times, but we don't want a formal charge, least formal charge on any of the elements. So what we can do is we can form something as bonding over here. So if we do that, what happens is this: S double bond O O So now this oxygen has no formal charge, it's now 0. Okay, this still has -1, this one also has -1. If you further check, you might think that S now has, you can again calculate 6 minus 4 plus 0, it again has +2 formal charge. Okay, so but now it's forming an octet. So if you go by the rule of octet, if you just want to see the octets and you don't want to go further, you will just say, okay, now it has S double bond O and OO, and that's done. And you can, for this you can have 3 resonance structure, that is S, okay, okay, and there's another one. Since these 3 oxygens are equivalent, we can have 3 resonance structures. Sorry. Yeah, you got 6. So similarly, in the last one, so we have 3 resonance structures. So in case, this will be the answer if you consider octet rule. But if you know sulfur is not in the second group, it's in the third group, so it does have, if you see sulfur here, this part in this periodic table, you will realize that sulfur is in the third row. Okay, so it does have the D shell, allowing him to extend his octet. So in that case, what we can do is we can get a formal charge on the element totally to 0. So what we can do is, instead of having this -1 and -1 on this oxygen and +2 here, we can move everything and we can form something like, now the formal charge on oxygen, all oxygens, is 0, as well as on sulfur it's 0. The only thing is that sulfur is not forming an octet now. In this case, the resonance structures are 0 because there's no resonance now, everything is equivalent. So in that case it will be 0 if you do not consider limitation. So preferably your answer would be A, because sulfur can form all the bonds with oxygen. So we'll again read the question and understand whether we are getting it right or wrong. The number of equivalent resonance structures connected with best Lewis structure of SO3. So the best Lewis structure definitely would be something like this. Okay, but yeah, it's allowed in exam. If you consider just an octet rule, then you might write 3 as the answer, but yeah, 0 is the answer for this. So moving on to the next question. Oh yeah, this question is missing some of the elements in my slides for some reason, so I will write down them first. So that's the structure. Now we are trying to understand the question. Which of the following are resonance structures of sulfur dioxide? So we have asked resonance structure of sulfur dioxide. So you will be following the same kind of method that you used previously in the previous question. The only difference is instead of SO3, you have something called as SO2 now. Again, going on with the same method, S has 6, oxygen has 6 multiplied by 2 because we have 2 oxygens, that is 12, you have 18 total electrons. Now S is the least electronegative, so you will keep S in the center. Further on you will make 2 bonds with oxygen, each oxygen. So subtracting 4, 2 for each oxygen, so you have 14. Now you know that oxygen, to form an octet, it can take only 6 electrons, right? So if we take 6, now it's already octet, so that we will subtract 6 2 times, that's 12. So what's left is 2 electrons. These 2 electrons will go on sulfur now because that's the only element left. Now if you check the resonance structure, for the resonance structure you will first check whether it's forming an octet. So you see that sulfur is having something as 6 electrons, it's not having 8 electrons. Also oxygen is having a -1 formal charge. Again, I can calculate if you want the formal charge on oxygen. It has 6 electrons in normal valence shell. Right now it has 1 bond plus it has 6 lone pair electrons, so it has a formal charge of -1. Okay, whereas sulfur has 6 electrons in valence shell. In a normal case, right now it forms 2 bonds and has 2 lone pair electrons, so it has a +2 charge. So we can write something as +2 formal charge. Going further, now our goal is to settle up this formal charge, right? So what we can do is we can move on and we can have something as, now it has +1 -1. Now if you check, sulfur is now in an octet form. Okay, it already has 8 electrons, so you can stop here, but the thing is you can see that the charge is +1 -1, so you can go further if you want and make it something like S double bond O, S double bond O. And here this is an extension of the octet rule. You have extended from the octet, now it has, as sulfur has 10 electrons. But if you see the options here, we don't have which of the following are resonance structure of sulfur dioxide. We don't have S double bond O and a lone pair. This might seem similar, but this doesn't have a lone pair, so this is not one of the resonance structure. So if we make resonance structure out of this, we will have something like double bond and single bond. So this is one of the resonance structure. I have drawn in a straight line. They are not in straight line because sulfur has a lone pair which will push both of the oxygens downwards, forming a trigonal planar state. So it will be something like originally, okay, and something like this. So our answer would be definitely second. This is not an answer because there's no lone pair. This is not an answer because oxygen won't form a pair bond like this. Okay, so what is left and what is true is 1 and 3. The options are missing here. So your answer would be 1 and 3 only. So moving further to question number 4. So here, let's read the question again. In the best Lewis structure of HCNO, what are the formal charges on C, N, and O? Note, the molecule has more than one central atom. So this is an important thing that you should know. It states already it has more than one central atom. In your exam and any other question, mostly if there are more than one central atom, it's mentioned in the question. So now we will try to make the Lewis structure to understand the formal charge. So let's see in HCNO, which one is the least electronegative? As we know, it will be the carbon. So we make a carbon in the center. Now, we also know the next one would be, it says the molecule has more than one central atom. So possibly the next one would be nitrogen. Now here's one thing that you might think that the oxygen and the hydrogen are bonded to each other in some form of OH, like this, like OH. But no, when it states that it's HCNO, it's indirectly showing you how they are connected. So you should know that the H is connected to the C, then the C is connected to the N, and N is connected to the O. This is the most general case. It happens that way when the name is given, but yeah. So now let's calculate for carbon. Here you go. Carbon has 6 electrons, and then we have nitrogen, we have 5 valence electrons. For oxygen we have 6. Sorry, again I made a mistake. Carbon has 4, and then hydrogen has just 1. So the total goes here to, I think, 16. Now what we will do, we will make the bonds. So we make a bond with carbon and nitrogen, then hydrogen has one bond with it, and we'll consider one bond with nitrogen and oxygen. Now we'll distribute these things. We'll first subtract the bond electrons. So we have 3 bonds, so multiplied by 2, that's equal to 6. We'll subtract that and it's 10. Once that's done, we will distribute this. So oxygen has, we can check how many electrons it should have. Let's not go to oxygen first. Let's see nitrogen. Okay, so nitrogen in normal state has, like, to form an octet it should have 8 electrons, but is it forming an 8 electron? No. So let's divide this 10 electrons. First we will give these electrons to oxygen, the outer elements. Okay, that's 6. Hydrogen won't have anything because it already had 1, and now forming a bond, its duplet is fulfilled. So the duplet is fulfilled forming this bond. So what's left is 4. So what we can do is, first we can put these 4 electrons on somewhere, like carbon or nitrogen, anywhere. But you know that carbon had 4, and in this bond it forms 4, or you can do anything, like you can make it on carbon or nitrogen. Considering I'm doing it on more electronegative element, that's nitrogen. Okay, so 1, 2, 3, 4. Now it forms an octet. You see that, right? 4 lone pair electrons and 4 bond pair electrons. But carbon is not forming an octet. It still has only 4 electrons. So what we can do is, hydrogen cannot give it more electrons. It can be done only by nitrogen. So nitrogen puts in more electrons, and we have something as a C triple bond. Now nitrogen won't have any lone pairs, but if you check, both nitrogen and carbon now has an octet formation. Okay, now we can check the formal charge on each one of them. So the octet is followed by each one other than hydrogen because it follows a duplet. Now you can check the formal charge. Again, I will write the formula for formal charge. That's equivalent to the valence electrons you had earlier minus the number of bonds, and it's in brackets, so you can write plus number of bond pair electrons. Okay, so first we'll check the formal charge in carbon because that's what is asked in carbon. So we'll write something as, what was the valence electrons? They were 4, so we have 4 minus number of bonds. It's having now 1, 2, 3, 4 bonds. And does it have any bond pair? No, it doesn't. So we have something as 0. So you can, if you want to, if you see in these options, it's only option A that has a formal charge on carbon as 0. So you can directly mark something as A. But it's better to check for the next elements. So we'll go for nitrogen. It has 5, and we'll write 5 minus how many bonds it has? 4. How many electron it has? Bond pair electrons? 0. So it has a positive 1 charge. So we can write, let me erase something over here so it's more clear. So it has a positive 1 charge. Okay, talking about oxygen, it has 6 electrons. 6 minus how many bond it has? 1. And how many electrons, bond pair electrons it has is 6. So it has a negative -1 charge. So we can write something as -1 over here. The overall charge on this element is still 0. So if you add up, it's 0 plus 1 minus 1, it's 0. I'm not calculating H because it's not asked, but even if you do H, it's something as, it had 1. How many bond it has? 1 plus 0 electrons, it gives you 0. So the overall formal charge is 0, but the individual charges is 0 plus 1 minus 1. So our answer is right, it's A. Moving to the next question. Okay, so what is asked is, what is the molecular shape of H3O plus? To understand the molecular structure, first you need to make the Lewis structure, if you know. So what we need to do is first understand what H3O plus looks like in Lewis structure. So let's see which one would become the central atom. Since H is a small atom, it doesn't become a central atom even if its electronegativity is less than oxygen. So we will make oxygen as the central atom, and plus there are 3 hydrogens, so we'll make 3 bonds. Oh yeah, we need to calculate the number of electrons. So oxygen gives 6, hydrogen gives 1, but we have 3 hydrogens, so it's 3. Plus there is a charge, plus charge. So we have to, what does that mean is there's 1 less electron, so we'll minus 1. So what we have a total is 8 electrons. And now we will subtract. Sorry for that interruption. So we'll subtract 2 for each bond. So it's 6 electrons, and now you have left is only 2 electrons. Okay, so these 2 electrons will go on the central atom. So now what you can see is that the oxygen is forming a octet, 2 lone pair electrons and 6 electrons in the bond pair. So once that's done, you see the structure, the Lewis structure is done. Now to understand what kind of molecular shape it has, you need to refer to something as this. So if you see, we have, I can open both of them together. So if you see, the oxygen here has 4 things, like 3 bond pairs and 1 lone pair. So we will have something as a tetrahedral structure. So it is total is 4. So we have to go and see in tetrahedral. But we know that there are molecular shape would be tetrahedral, but we have to see how many of them is bond pair and how many of them are electron pairs. So we know there are 3 bond pairs and 1 electron pair or lone pair. So what we have is trigonal pyramidal. So if you see, I can't mark it in that thing, but yeah, it's something as it's in tetrahedral part, and it's 3 and 1, so it's trigonal. Let me try it. Let's see, can I do that? No. So I will continue like this. So it's trigonal pyramidal if you see that way, and it's trigonal middle. Okay, so it's the answer goes out to be E, trigonal. So this arrangement of molecule is helpful. You have to remember this. You won't be given this in the exam. And yeah, so first what you do is you see how many bonds you have, lone pairs and bond pairs combined, and then you go inside and check which one will be it. So how it looks, it will be looking something like O, hydrogen, hydrogen, hydrogen with a lone pair, and the overall charge on this is positive. Okay, so I'll close this window now and we'll shorten this up. Moving on to the next question. Here again some things are missing, so I will write it down. It's CS. This might take some time. These are iodines and they have 3 lone pairs on each one, and this one is chlorine, oxygen. Here you go, C, N, and next one is NO2. So this is A, B, C, D, E. So now I think I haven't missed anything. Oh yeah, it's negative charge. Again here it's negative charge. Now let's see what kind of structure they are having. So what is asked? Which of the following molecules is not linear? So a general law says that if something is having a double bond or triple bond, the bond is restricted from rotating. It doesn't rotate. So you can directly say that you can, or I think you don't need to understand that part, so I will take back my words. Let's not go into that right now. We'll just go one by one and see what kind of structure each one has, whether they do have linearity or not. So let's go with first A, that is S double bond C double bond S. So if you see the central atom, that is carbon, it has just 2 bond pairs. Okay, it's having this is considered as 1 bond pair. Okay? 1 bond pair and the second bond pair. Okay, because it's made between the 2 elements itself. There are no lone pairs. So now you can use the same thing that we used earlier. You can check if you have just two pairs, you will be having a linear structure with 180 degree. It stays linear. Okay, so moving on back. So this will form linear. Next would be B. So we have something as chlorine with oxygen, but let's make it directly the Lewis structure we need to see. So it would look something like chlorine with oxygens, and there are two lone pairs, sorry. So this one has 4 pairs, total pairs, 2 bond pairs and 2 lone pairs. So if you check again, I will open it sideways this time, so it's much easier. Let's do it. So if you see, for 4 pairs, it will form something as a tetrahedral structure, and the molecule won't be linear. Definitely it won't be linear. Why? Because if you see in the 4 part, it's written molecular shape, it's bent. So can I do that? Let's see. No, I can't. So it will be bent. If you see in tetrahedral part, you go on in molecular shape, there are 3 options: tetrahedral, trigonal, pyramidal, and bent. In the bent, you can see that this condition matches. It's 2 bond pairs and 2 electron pairs. So this will be bent. So you can stop here and just say that okay, it's bent, so B is the answer. But let's check for C, D, and E and how they are linear. Let's do that. So let's see the question for C, and we'll make it smaller. So this one is N. You have oxygen, and you don't have any lone pairs. So again, you see there are only 2 pairs, and that is bond pairs, so 2 bonds pairs. So it will be again, the only option with 2 bond pairs is linear. If you see on the left side, molecular shape is again linear. For the question D, like the option D, you go on and you make something as I, and you have, let's make it something like this. I will rub it and make it somewhere else. Let's do it here. So I, and I, it forms something like, I'm doing it directly, but I will show you how I did it. So if we don't have it here cleanly stated, but let's see. Okay, so for 5 it's trigonal pyramidal, but if you see that this one is forming, if you see that I don't have that in my slide here, but if you see in iodine structure, it has 5 pairs, that is 2 bond pairs and 3 lone pairs. And for that structure you have trigonal bipyramidal, you can see for the 5, and this I bonding is creating an angle of 180 degree. They're totally in opposite direction, so this will be linear. Okay, now checking for HCN, again HC, and no lone pairs, so just 2 bond pairs, so it will be directly linear. So our answer is definitely B. Now going to the next question. Here we go. When the molecules H2O, CH4 and NH3 are arranged in order of increasing bond angle, the correct sequence is. So what we are focusing right now is 3 molecules, H2O, CH4, NH3, and increasing bond angle. So we have to compare their bond angles, the correct sequence for that. So what we can do is first make the Lewis structure and see what do we have. The molecular structure can be known. So let's go first with H2O. So I'm not going again and again in the same method. You will use the same technique to form the structure. So it's something like, so oxygen is forming an octet, you can, I will again show you once only for this question. So it's oxygen with 6 electrons, hydrogen 2 times 1 electrons, that's 8. Then we have 2 bonds, so you have -4 and you get 4. These 4 are the lone pairs that I have shown you. Okay, so this is the kind of structure that we have. For this, just make something like called as lone pair kind of things. And if you see that this one has 2 bond pairs, 2 lone pairs, total is 4 for sure, so it will be something as tetrahedral. You can see the previous table again and show you something as this tetrahedral structure. And if you see the bend part shows you that there are 2 lone pairs and 2 bond pairs, so the angle would be something as less than 109.5, approximately 109.5. So what we can do is we can write that down. So it has an angle less than 109.5 degrees. Okay, next we will see for CH4. I'm not doing the same calculation again, it's simple. So we will have something as CH4 and there is H. So this again is tetrahedral, 4 bond pairs, okay, and 0 lone pairs. So this will be the difference here. If you check again, this is different. This one is purely tetrahedral. If you see the example itself shows you CH4, it's tetrahedral and it exactly has 109.5 degrees. So it's not less than 109.5 degrees, it's exactly 109.5. So let's make it. So we have for this one CH4 is 109.5 degrees. Next one we have is NH3. So let's make NH3 now. And H, there is 1 lone pair. And if you see in the left side of the slides, NH3 forms trigonal pyramidal. It's tetrahedral, definitely. It has 3 bond pairs and 1 lone pair. So it total is again 4. All 3 of them have 4 electron groups, but out of them they have different combinations of bond pairs and lone pairs. So this will be forming something as trigonal pyramidal. Okay, and the angle is still 109.5 degrees. Now you definitely know that this angle is highest because other two are less than 109.5. So you can say the CH4 would be the first. You will say that CH4 is something which will be having the highest angles. But what is asked in this is, when the molecules are arranged in order of increasing bond angle, the correct sequence is. But if you have something as less than 109 between these pairs, the angle is less than 109.5. Okay, but if this decreases, this angle definitely increases because that gives more room for the lone pair. So the actual reason why these angles are less than 109.5 degree is that we use the valence. I will tell you, it's valence, VSPER, that we call valence shell electron pair, VSEPR, valence shell electron pair theory. So what we have is that what it says is that the bond pairs and lone pairs repulsion acts differently. Okay, so what I will do is I will just rub something from here so that we have some clean space. Okay, so it's something like this. I will change the color to. the repulsion between these lone pairs is higher repulsion compared to this, that's bond pair. So this is okay, lone pair repulsion. This one is lone pair bond pair repulsion, and this one is bond pair repulsion. So writing it as LP for lone pair and BP for bond pair, you can say that the lone pair repulsion is higher compared to lone pair bond pair repulsion, and the least one is bond pair repulsion. VSEPR. So what happens because of this is the highest repulsion between these two bond pairs forces this repulsion forces this lone pairs to move aside and forces the angle between these two edges to decrease at less than 109.5. And this is why now you can use this method to understand how the biggest angle in this pair would be somewhere here, right, between these two bond pairs, and it would be definitely more than 109.5 degrees, whereas in this CH4 all angles are 109.5 degrees. So we can say that now what was asked was arrange in order of increasing bond angle. Okay, so here the bond angle in H2O is much greater than the bond angle in CH4. Okay, so now checking for NH3, here we just have one lone pair, so the repulsion is higher compared to a bond pair. Okay, let me change the color again. Repulsion would be higher compared to this bond over here. Okay, so definitely the angle would be greater than 109.5, but this repulsion, as we know from this theory, will be less compared to this repulsion here. That's why the angle between H2O, that is the two lone pairs, will be higher compared to NH3 compared to CH4. So your answer comes out to be B. So this is indirectly shows here, you can indirectly connect here. In H2O we have lone pair repulsion, in NH3 we have lone pair bond pair repulsion, and in CH4 we have bond pair and bond pair repulsion. Okay, so that's what we are trying to do. Now moving on to the next question. So if you still have doubts in this, you can email me, and the very first I had written my email ID. You can email me, I can describe it in more detail. Now going on to question number 8. Reading again the question, which one of the following molecule has the highest angle? So between the adjacent bonds, here now we will be again using the VSEPR theory, but we might be going further beyond the VSEPR theory also. So let's make the bonds first, like let's make the elements Lewis structure. So it's written C is the central atom, so the most easiest way is make everyone Lewis structure and compare them. So C double bond O. Then we will make something for CH4. It's H, we already made it in the last question. Then again H2O we have already done before, so it's something as O H. Okay, and then we make something for NH3. So these questions are nearly the same. Okay, and last one is P H and H. So for P, you know that it belongs to the same column compared to N, so it will have the similar kind of structure with hydrogen. Now what is the question? Which one of the following molecule has the smallest angle between adjacent bonds? Smallest. Okay, we have to go with smallest. Here we have straight 180 degrees because it's linear. Here we already measured in previous question, that's 109.5 degrees exact. Here we know it's less than 109.5 degrees. Okay, now we also know that this angle is highest, right? We measured previously that the angle between H2O is higher than NH3. That's what we did here. Okay. And you can also say that it was higher than CH4, but here comes the question. So this is also this angle in between adjacent bonds. Okay, so this one is less than 109, but this one is greater than 109.5. Similarly, this one is greater than 109.5. You can think that even P, that is phosphorus, would have similar thing, greater than 109.5. So let's understand what is difference between pH3 and NH3. So if you know that N is in the second group, P is in the third group. Okay, so the N is much smaller in size, N is smaller in size, P is bigger in size. So what happens is that the elements, the bonds between N and H are much closer. Okay, whereas in P they are farther because P itself is big, so there's a repulsion between them, electron clouds, and it's far away. So when the H atoms are close by to each other, what happens is that they repel each other much more. Okay, they repel each other too much. Okay, now here in compared to pH3, we again have something as lone pairs. Here they're far away from the P, so that's why the repulsion is not as strong as in compared to NH3. So what we can say that this angle, so angle, okay, I should make it more clean. This 2 angle and 1, so this angle 1 would be smaller compared to angle 2. Why I'm saying that, you can just, it's simple geometry. So for example, I make a center point and there's something, as I said, that the repulsion between H and H in N would be bigger compared to H and H in P. Because of that, the angle here in this one is smaller compared to the H bonding between H repulsion between N. So it's something like this. In N it's something like this, H, and N, whereas in P they go much further away. So even if the gap, this is just trying to make you understand in form of geometry, the gap is same between H and H, the angle angle 1 is smaller compared to angle 2. Okay, so that's why we would have the smallest angle. What's the question? Which one of the following molecule has the smallest angle? So this angle we have, wait, sorry for that. Okay, it went all the way back. So yeah, so some angles in H2O are bigger than 109.5, some angles are 109.5, less than 109.5, and in the only thing is when you have H2O, this angle is greater than 109.5, but this angle is less than, so we have to go with the smallest angle. We have to find the smallest angle. So this is smaller, even this is smaller than 109.5, but we know that the repulsion caused by these bond pairs would force these two hydrogens to get closer, but that repulsion is will not make even it that strong, because I'm sorry for that. Okay, so the comparison now comes down to NH3 and PH3, because that's the angles where we are trying to understand, and we already told that N and H are closely related, they are very nearby, so the angle 2 would be bigger compared to angle 1, so your answer would be PH3. Don't get confused with this or the previous question that's here. The difference between these two questions is we had to find the highest angle, okay, highest angle possible, and here we have to find the smallest angle possible and not the highest angle possible. So the smallest angle possible is between PH3, in the PH3, between the angle this one, this. So that's the answer. Now moving to question number 9. Let's read this question, and what we have is, which of the following best describes the shape and polarity of carbon disulfide? What we have to ask is shape and polarity. So just marking the important lines in the question, and that's CS2. It's already mentioned. Again, C is the central atom. You need to find the molecule, so we'll again make C as the central atom, and we'll make single bonds. You know, again doing the normal calculation, it's 4 electrons. Sulfur has 6 multiplied by 2, that gives you 12 plus 4, that's 16, and you made 2 bonds, so it's 2 into 2, so it's 12. Now you can give the 6 electrons to sulfur, 6 each. But now check for the octet of the central atom. Does this form an octet? No, it has just 2 electrons, right? So 2 bonds, so it has 4 electrons. So what we can do is, what we get, something like this. Now the octet is followed. We can check the octet for sulfur. Yes, it's following. So now checking the molecular shape and polarity. So what we can do is we can check, you know that it's linear. So how did I do that? I'll show you here. Here we have only 2 electron groups, so it's 2 linear, it's 180 degree. Okay, so it's linear structure, so what we have is linear. Okay, but there are 2 options, linear, and there is polar and non-polar. So now we will check whether it's polar or non-polar. So if something is linear, consider here, again I am making it again. So we know that C is less electronegative compared to sulfur. So there will be a charge moving on in this direction and in this direction. But since we know the angle between this is 180 degree, the molecule itself will cancel out each other, the charges. So they are in equal and opposite direction. Okay, and again make it in blue, equal and opposite. So it's something as you are 2 horses pulling something in opposite direction. So what happens is the overall polarity is 0. That means it's non-polar. Okay, so even if the C and S bond is polar, the overall polarity is 0, that is non-polar. The CS2 molecule is non-polar. So next question. Now we are trying to move into something as spectroscopy, and it's something you did 2-3 weeks back. Let's read it. In visible, not invisible, it's invisible spectroscopy, standard solutions containing the substance to be analyzed are used to construct standard curves. So it's something talking about standard curve spectroscopy. A standard curve is used to determine which of the following properties of the substance. So if you remember that we tried to make a standard curve, what was it? It was something as like this. We were trying to measure the absorbance of different standard concentrations. Okay, and we plotted some points like this. Okay, and then we created a line that was like nearly passing through everyone. Okay, and it was a linear line and we named it as y equal to mx plus c. So if you remember, this y is the absorbance, the x is the concentration, this c, I'm making it something as d because you don't get confused, this is something which is just this part. Okay, and the m used to stand is equivalent to something as molar absorptivity. Okay, so you can do the same thing with compare it. If you don't understand it directly, what I'm trying to say is something absorbance is equal to molar absorptivity multiplied by path length multiplied by concentration. So if A, that is absorbance, is y, molar absorptivity I'm writing as again same, path length was 1, you know, and the concentration is something as x here, so that's x, so it's y lambda x. So we can say that this, compare this equation and this equation, there's some error in this, considering there's an error, so let's consider that error to be this. So when you compare these two equations, the slope, that is m, is the molar absorptivity. So whatever slope you get from the standard curve will be your molar absorptivity. Sorry for that. Okay. So our answer is E. Okay. Moving to question number 11. This is more of a theoretical question, but I can try to show you what it means. So the question says, in visible spectroscopy, the wavelength at maximum absorbance is usually used for spectrometer analysis. Because, so let's understand this question first. The wavelength at maximum absorbance is usually used for a spectrometric analysis. So what we are trying to do is something like, if you remember, we are trying to measure the absorbance. The first thing that we are doing to find the maximum wavelength was wavelength, and we got something like, and we are trying to find what was this wavelength, that was our lambda max. So the question states, is asking indirectly, why do we measure the absorbance at this lambda max? That's the question. So think about it. Let's read the options. So first option says the change in absorbance per unit change in concentration is largest at this wavelength. So it's trying to relate the absorbance to concentration. So which formula relates absorbance and concentration? We know it's the Beer-Lambert's law. I already wrote it here in short, so I will write it again. It's absorbance E, B, C. We write it directly. So B is the path length, concentration, and molar absorptivity, and this is absorbance. Okay. So what is asked is, in visible spectroscopy, the wavelength at maximum absorbance maximum absorbance is usually used for a spectrometric analysis because, now let's see, the change in absorbance per unit change in concentration is largest at this wavelength. Okay, you don't get it easily what it's trying to say, but it's relating something to absorbance and concentration. Okay, next, the change in absorbance per unit change in concentration is smallest. It's saying this one says it's largest, and yes one says it's smallest. Okay, chemical substances only absorb visible light at a single wavelength. So this is not true, because if you see in this absorbance chart, the elements are still absorbing somewhere here. It's absorbing even here. So this is definitely not true. Chemical substances absorb visible light equally well at all wavelengths? No. So if you see, it's having the highest over here. So even D is not the option. So what's left is A and B. Now, the change in absorbance per unit change in concentration is smallest at this wavelength. So trying to understand this, so it's trying to say that the change in absorbance would be smallest. So if we change the concentration, let's do something like this. So for option B, okay, if we change the concentration, there will be only a small change in absorbance. But if you remember, our goal of doing the spectrometry analysis was to measure concentration. Okay, so goal was this concentration measurement. So if the change in absorbance per unit change in concentration is small, then this is not good, because for example, if we have something as consider the absorbance, the concentration is changing from 1 molar to 2 molar, and the absorbance do not change much. Okay, consider it's like changing very small, or it's not changing. Is that good? No, because like we want the absorbance to change. We want the absorbance to show that the two concentrations are different. Okay, that's why this thing is wrong. Now checking the first option, the change in absorbance per unit change in concentration is largest. So what it says is that if we get change from concentration, something from example 1 molar to 2 molar, there will be a big change in absorbance. Okay, that's what we want. We want to see a minute change in concentration should show up as a change in absorbance. So we can say that A is the answer. The other way you can think of doing is through mathematical analysis, where you just add like a change in concentration. Let's see, it's something like A plus considering D as the error. Okay, and you have C. Now you'll see that how a change in absorbance is affecting the concentration. So if you redo this thing, and it becomes something as A by EB plus D by EB. Okay, so now if you put in the first meaning of the first one, for A, option A, the change in absorbance per unit change in concentration is largest at this wavelength. So what it's trying to say, if we change the absorbance, it will show its impact on concentration very broadly, like heavily, and that's what we want. So yep, A is the answer. Okay, and if you want to understand more of the mathematical method of this, I can show you that, but I don't think it requires here. So what it's trying to say, again I will go in more detail. You can go further if you don't want to read through this mathematical part. So for the mathematical thing, let's rub this, clean this space, and let's do change in absorbance per unit change in concentration. So having absorbance on the top, the concentration on the bottom. So our goal is something as EB, and this is the same thing as this formula. I just moved on something. So what it's saying is the change in absorbance per unit change in concentration is largest at this wavelength. So this is what it's trying to say, that if we change slightly the concentration, there will be a large change in absorbance. Okay, I think I should stop here for this question, and so the answer is A, and move to the next one. Okay, reading the question again. So which correctly lists the nitrogen oxygen bond length in NO plus Cl NO? It's Cl, it's chlorine. Okay, it's not carbon, iodine, and nitrogen and oxygen. No, it's chlorine, nitrogen, and oxygen. And the next one is HO NH2. Note, for all three molecules, N is the central atom. So it's already given. Let's make the structure in general. So what's asked is bond lengths. So you have to tell the bond lengths. Okay, so let's do this. Let's make their structures. So N, again, N stands for 5 valence electrons, oxygen has 6, minus 1 for the positive charge, and you have 10. So we will make oxygen bond here. We will give the 2 electrons gone, so what's left is 8, and we will give 6 electrons to oxygen. Okay, and that's left is 2, so 2 electrons to nitrogen. Now you see that N is not fulfilling its octet, so you have something as N triple bond O. So here you see that both of them are forming an octet, but you see that oxygen right now has a formal charge of what? Let's see the formal charge on oxygen. It's 6 minus, again I'm using the same formula that I used earlier. 3 is the bond pairs, and plus 1 is the lone pair. No, 2 lone pair electrons, so it's 1. So there's a positive charge 1. So that's what is there. It's positive 1. So the overall charge of N is plus 1. Okay, next we have chlorine, nitrogen, and oxygen. We can do the same thing. Chlorine has 7 electrons, nitrogen has 5, oxygen has 6. You go on adding some all of this, you have 18, 2 bonds, so 4 minus, you have 14. You give electrons first to chlorine because it's highly electronegative, so 6. Similarly 6 to oxygen, and what is left is 2, so 2 to nitrogen. Now if you see properly, the nitrogen is not forming an octet again, so we'll give the electrons from oxygen. Now why from oxygen? Because oxygen is less electronegative, so it can give oxygen electrons. So we have Cl. Now if you see, the formal charge is 0 and octet is followed. Okay, so we have the structure for Cl and O. Next we will make the structure for HO NH2, that is N as the central atom, 2 H bonds, and the next one is OH. So it's stated HO, so it shows that it's an HO bond. So nitrogen has, you can do something like H. Okay, so nitrogen has 5, oxygen 6, hydrogen 1 multiplied by 3 because we have 3 hydrogens, so it goes to 14. Then we have made already 4 bonds, so that gives you 10. Okay, we will give how many electrons to oxygen, so we will give, now it forms an octet, oxygen is forming an octet, so that goes -4. And did I miss something? Okay, let's see. Oh, I didn't subtract. Okay, so 4 bonds, but each bond equivalents to, sorry for that, each bond equivalents to 2 electrons, so it's 8, so it's 14 minus 8, that is 6. So 4 electrons to oxygen, so that's remaining is 2, so that will go on nitrogen. Now if you see, nitrogen is fulfilling its octet, oxygen is fulfilling its octet, and it's done. So now compare 1, 2, and the third one. Okay, we want to see the bond length. So now you don't need to measure the bond lengths, you don't need to remember them. What you can do is simple. A single bond is bigger in length compared to a double bond compared to a triple bond. Okay, so we are trying to see a bond between nitrogen and oxygen, right? So here in the first one, this is triple bond between the same nitrogen and oxygen. Here it's double bond, but here it's single bond. So if you have just one bond between two elements, they will be a bit far away. Okay, but if you try to form the second bond, they have to come closer. Okay, for the third bond, you will come even closer. So the more you are tied to each other, the smaller the gap between you. So using this thing, what we can say is the length between N and O bond will be highest for this single bond. So highest bond length for N and O. So what we can say is that HO and H2 would be having the highest bond length. So if you see, there are 3 options, 144, 120 and 106. So you can check which one has the highest bond length here, or you can, let's go one by one. So we can say that NO plus, as I said, triple bond will have least bond length. So then it will be, next will be ClNO, then it will be highest bond length will be with HO and 2. So bond lengths. So check which one of the options follows this trend. So 144 for option A, 144, 120, no, it's opposite. So this is not the answer. B, 120, 106, no, 106 should is the right thing, because the bond length for Cl and O would be greater than NO. So this is not the option. So if you go on, you check, you will find that E is the only one. You can see 106, then you have greater 120, greater 144. So your answer is E. Next question. It's 13th question. So which one of the following molecule or ions has a trigonal pyramidal molecular geometry? Okay, so it's asking which molecule has a trigonal pyramidal geometry. So let's see. You see, it's trigonal pyramidal. In one option is in tetrahedral trigonal pyramidal, and the other option is in that electron group of trigonal pyramidal itself. So there are 2 possibilities. So let's move on back to the question. Let's make the structures. I'm not wasting too much of time in making and counting the electrons, just doing it. So oxygen, and you have here there is a slightly positive charge, here negative charge, and there's a resonance structure. Sorry. So this is the resonance structure of O3. How I did it, if you want to do again, just you have 3 oxygens, 3 into 6, that's 18. You form 3 bonds first, so it's minus 6, that's 12. Then you give, okay, I will draw it again. So it's something like this. You made 2 bonds, right? Make 2 bonds, so it's 2 into 2, that's 14 left. Then you give these electrons to oxygens, and the remaining 2 electron goes to this oxygen. So you see that there's no octet formed in the central atom, so you give this electrons to it. What happens is, now there's an octet formation. Now one can ask, why not this given electron and like form a double bond and not have a formal negative charge here? Okay, because if you see, this oxygen is having a formal negative -1 charge. At the same time, oxygen in the center has a formal negative positive charge, sorry. Okay, but why it can't form? Because the octet is already fulfilled, okay, in the central oxygen. And since oxygen is in second row, it doesn't have the ability to further extend its octet. Okay, so it can have just 8 electrons in the valence shell. So that's why this is the final structure. Okay. Now I'll rub it. So this is the structure. So if you see this structure, is it trigonal pyramidal? No, this one is more of, it has, sorry, this is something like this, right? So it has 3 electron groups. If you see 3 electron groups, let's get it to, okay. So if you see, this is 3 electron groups. In 3 electron groups, you don't have any option as trigonal pyramidal. So A is not the answer. Okay. Next, make B, that is BF3. This is much simple. It's written already. B is the central atom, and you just make 3 bonds. Let's again do the same calculation. Boron has 3 electrons in the valence shell. Fluorine has 7, that's 21, goes 24. You have 3 bonds formed, so it's 6, 8 in remaining, 6 on each one of the fluorine, and done. 0. So it again has 3 electron groups, 3 electron groups. So BF3 is also not the answer. Next goes PF5. Okay, where P is the central atom. Okay, okay, so F. So the trigonal pyramidal, sorry, in the earlier discussion I said that it's possible with electron groups of 5. No, because it says trigonal bipyramidal. We have to think of something as trigonal pyramidal. That's only possible in tetrahedral, and that too when we have something as 3 bond groups and 1 electron group. So here in PF5, it's 5 electron groups, so you can directly negate it out because it will form a trigonal bipyramidal, not a trigonal pyramidal. So C is not the answer. Next, moving on to XeF3. So here let me show you what XeF3 looks like. First I will erase the earlier calculations so you know what we are doing. Okay, so let's do XeF3. I'm keeping the left side open. So we have Xe that has 8 electrons. So if you know that Xe is a noble gas, so it will have an octet already fulfilled. So it's 8 valence electrons or a fulfilled shell. Then you have F that gives you 7, and we have 3 fluorine, so it's XeF3 plus, right? It's 21. Plus we have a positive sign that shows as 1 less electron, so we have right now 28 electrons. Now what we'll do is we'll keep Xe in the center. We'll form three single bonds with 3 fluorines. That gives you 22 electrons are left. Then we will give 6 electrons each to fluorine. What is left is 4. These 4 electrons will go on Xe. So again, if you count, we have 1, 2, 3, 4, 5. 3 bond pairs and 2 lone pairs. So in that way, what's happening is we have 5 groups. And if you see 5, it forms trigonal pyramidal. So that wouldn't be an answer. Trigonal bipyramidal. So XeF5 is not the XeF3 plus is not the answer. So generally by that rule, E is the answer. But let's see how do we make its structure. So let's make the structure for oxygen gives you 6, hydrogen gives you 3, and it's H3 plus, so H3O plus, so it's -1, so it gives you 8. I think we have made the structure earlier, but still I will make it again. So oxygen is the center, H, 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 that gives you 6, remaining 2 electrons. So if you see now, it has positive charge for sure, 4 electron groups, right? So it has 4 electron groups. That's tetrahedral. Okay, plus it has 3 bond pairs and 1 electron pair or lone pair, and that exactly is the requirement for a trigonal bipyramidal, if you see on the left side. So our answer is H3O plus. Now moving to 14th, based on, okay, so here this sign indirectly represents a degree, so it's 60 degrees. It's just a problem with the software. So based on the VSEPR model, so I already stated that it's valence, shell, electron, pair, repulsion. Okay, so what is asked is, based on this, the HOO bond angle in H2O minus would be expected to be closest. So if you see all these angles, they are nearly close to the angles that are mentioned in this. So if you see, it's 120, 180, 120, 109.5. So that are the kind of angles that we have. Let's open it again. So let's, like, if we know the structure of HO2 minus, we will also know the angle. Okay, and it's asked the closest, it's not asked exactly, so it's closest. So let's make the HO2 minus. So O has 6 H, but we have 2 oxygens, so it's 2L, and there's 1 O plus, we have a negative sign, so it has 1 extra electron, so 1, so we get 14. Now since we know oxygen would be the central atom because H can't be the central atom, so O, we will form one with H and the other will be O. So yeah, now we form 2 pairs, 2 bonds, so it will be -4. It's 10 remaining, so we will give 6 electrons to the outer oxygen first, and what's left is 4, so we'll give 2. Now check sorry, I was drinking water. But now check, do we have a formation of octet? You see the central oxygen? Yes, it does. Plus you can see there's a formal charge on this oxygen because it has 7 electrons, so that's where the formal charge -1 is coming. Now if you see what kind of molecular structure this will have, we will check for the central atom. So we have, this one is 1 lone pair, 1 lone pair, so we have 2 bond pairs, 2 lone pairs, that is total 4 electron groups. So if you remember that 4 electron pair groups, let's again go to this one, the 4 electron pair groups give some angles that are closest. It says closest to 109.5, not to 120 or 180. So your answer would be 109.5, not 120, not 180, not 90, not 60. The 90 and the 60 degree angles are mostly where the electron pair groups goes in not 60 but at least 90 in trigonal bipyramidal, and beyond that, that is for 5 electron pair groups. We are not studying that. So yeah, C is the answer. Moving on to question number 15th. So let's do it. Which row of the following table contains correct information about lead chloride? So if you want to see what lead is first, how many valence electrons are, you might not know that. So let's go and see. So if you see lead, it's in group number, column number 14, and its atomic number is 82. So it's somewhere 82. So if you check, its structure would be something as, let's write it down. So it will be, I'm writing the condensed structure, Xc 4F14 plus 5D10 and then 6S2 and 6P2. So how I did this, so if you see, I can't mark it down their way, but yeah, there are in the 6th row there are lanthanides. That's why all the 14 electrons in the F shell are fulfilled. Then the D shell are fulfilled because of the D orbital groups. And then what we have from the 13th column is getting into the transition elements. That's why we have this kind of electrons are placed in this order. So now let's see, we can see that it has 2 or I would say like 4 electrons in the valence shell. So let's say PB has 4. This can't be used because they're already fulfilled. Then PB has 4 and Cl has 7. We have 2 of such chlorines, so it's 14. Total becomes 18. So now let's put PB here, Cl, Cl, right? Now 2 bonds formed, so it's 4, remaining is 14, giving 6 electrons each to chlorine to fulfill its octet. What's remaining is 2, giving these 2 electrons to lead. Now you can see that PB is not forming an octet here, it's not. Okay, so what we can do is we can check whether it's okay to do that. So I will just make it again here. It's very clumsy over there. It's Cl, so whatever may be the case, okay, so even if it's forming, like you can consider that the chlorine is giving it an electron and forming a chlorine Cl, which is less likely, it's not possible because chlorine is very highly electronegative, but still considering it does do that, still we have 3 electron groups. Okay, and for 3 electron groups we know that, let's go back to this thing. For 3 electron groups we know that it's trigonal planar, plus if you checked earlier we had 2 bond pair groups and 1 electron pair groups. So what we can say that, let's open it side by side, that the electron geometry would be trigonal planar. So E and A options are out already. Next we check the type of molecular shape. So since it has 1 bond pair and 1 electron pair or lone pair and 2 bond pairs, we know that it would be a bent structure. If you see under trigonal planar, it will be a bent structure. So what we have is we have a bend structure, so the possibility now reduces to only C and D. Next, it says that the angle would be less than 120 degrees. Okay, so the only option is C is saying 120 degree exactly, so C is not the option, only answer is D. And you don't need to like check further, but yes, let's see whether it's polar or not. So you know that, let's get back to the bigger screen. You know that chlorine is more electronegative, so it will pull electrons towards itself, and the overall resultant polarity would be something like, so if I consider this as PB, the overall polarity would be something downward. So yes, this is polar, so your answer is D. So we got the answer for 15th one, that's D. So we are done with the part A now. If you have any other question, you can directly contact me at my email ID, and please let me know. I hope this was useful. Thank you.